Hey guys, welcome to Making Waves with Python number 2. This is the second virtual meeting that we're having this semester for the Making Waves project. It's part of the UIC EMBS chapter. Hopefully you guys weren't stuck waiting around. I did have plans to record this video sooner. Unfortunately, I did get sick, but thankfully now I'm feeling a lot better, good enough to record this video. So I'm going to share my screen and go ahead and get started. So, as you can see, second edition of Making Waves with Python. And before we move on to the bulk of this video, I do want to go ahead and explain some bit more basics, specifically about channels and extraction. And over here on the right, this is kind of just how I imagine all of us are feeling. And I know I am feeling this way at this point in the semester. Kind of gets a little harder when you get closer to the end, but what can you do? So, working with channels. The sample data that we worked with previously and that we're working with this video contains 3 different types of data: MEG, EEG, and EOG. And we have 3 different types of data, and each of those types of data have many different channels. So sometimes we only want to view a few of those channels or alter the channels that we do have, as well as access information that is contained within those channels. Thankfully, M&E has a lot of ways that come with a library to do that already. And we can access a lot of that information using the info object. So as you can see in the top commands right here, if we access the raw info object, we can print any information that was stored in the BADS variable, which in this case is any channels that were marked bad during acquisition, which M&E does automatically. We can also print the sampling frequency and any miscellaneous info that's important, that might be important to know about how the data was acquired. So let's see. Perfect. So I'm going to be I'm going to try to run the code live here. So hopefully everything goes well. So as usual, when we run the code, there is a couple of things that we need to do first. I'm going to go ahead and just copy and paste this code. But we need to import a couple of libraries, such as OS, in this case, some NumPy, Matplot, and of course, M&E. And in this case, I'm also going to import a couple of other libraries we might end up using later. And we also, of course, need to access the data folder and load the sample data. So in this case, I'm creating a raw variable to open the raw data. And if you might remember from last time, we can also go ahead and print the actual info object. So we can print using print raw.info. And this will give us a bunch of information about the data that we've just uploaded. So in this case, you can see that there's 4 items here. There's a low pass filter, 376 channels, projections, sampling frequency with 600.6 hertz. And of course, we can also print out individual things. So as we saw, there is a print bad channel. There is a BADS object, which we can use to print out a list of all the channels that were marked bad. In this case, we have 2 channels that were marked bad, MEG 2443 and EEG 53. We can also print out just the sampling frequency as opposed to printing out the entire info object. So our sampling frequency, as you can see, matches over here, 600.6 hertz. And we can print out any acquisition info that might be important to know. So in this case, this data was acquired using the vector view system at NMR-MGH. And there's also functions in M&E that allows us to pick specific channels or alter the channels that we are using. So in this case, first things first, I'm going to create a temporary variable using the .copy function so that any changes we make to the channels in the temp variable won't affect our original variable. So M&E, one thing it doesn't do, it doesn't actually count the number of channels that you have. But what it can do, and what we're printing out here in this command, is it can count the number of channel names that there are. And given the number of channel names, assuming each channel has its own name, we can print out the number of channels that way. So in this case, print length of the channel names list. And here we get 376. We can also drop certain channels. The command is pretty straightforward, and you can see it over here on the right. we just access our variable raw underscore temp dot drop underscore channels, and then we enter the channels that we want to drop. Earlier, we saw that our EEG53 was a bad channel during acquisition. So maybe we want to go ahead and drop that channel. So we just enter this command. We can get kind of this little confirmation. And if we go ahead and run the same command we did earlier to print out the length of our channel names, we can see that now we have 375 channels, kind of just confirming that we did in fact drop the channel. We can also use these functions to only view certain channels. So in this case, if we only care, we're using the .pick underscore channels function, and we're entering the same commands, the same arguments that are here. We're entering a list of the channels that we want to view. In this case, MEG 1811, EEG 17, and EOG 61. Again, we'll get a little confirmation. And then if we print the length of the channel names, you can see that now we print out only 3 channels, since that's the only thing we care about. So moving on, a little bit more about working with channels is that each channel has its own specific name, usually just numbered. However, we can change that. And each channel has its own type, which you might not necessarily need to know how to do or need to use, but it makes it easy to identify things if needed, as well as verify channel types or change it. So you can very easily change the channel name in M&E using this command right here, which is accessing the variable, in this case raw or raw underscore temp dot rename underscore channels. And then you enter the arguments. Oops, sorry about that. So in this case, we're renaming the EOG 61 channel and renaming it to be blink detector. We can also do the same thing if we had a channel that we knew was a stimulation channel. We could change EEG channel 01 into the stimulation channel. So that's a pretty simple command. We can also check the channel type and change its channel type. Although if you record your data and acquire it properly, you probably won't need to do this. But so we can do that by running these 2 commands right here. Raw.set channel types. In this case, we take EEG channel 01 and turn it into an EOG type channel. So I'm going to go ahead and run that command. Get a little confirmation. And then if we go ahead and run the command underneath, print, we just get a list, kind of just confirming that we did in fact change the channel. So here we printed out we can see that we printed out the EOG type channels, and we can see that EEG01 is now an EOG type channel. We can also limit the data that we actually want to see. So the data arrays tend to be pretty long, and sometimes you don't need to see all of it. It also just saves some space. And you can limit the time domain by cropping the signal using the .crop function. So in this case, we're going to create another variable called raw underscore selection. And we're going to create a copy so that we don't alter the original data. So raw.copy parentheses .crop, and this is where we enter our arguments. So in this case, we're going to crop our data starting from 10 seconds and have it last only 12.5 seconds. And then we can print this just to confirm that we did in fact have it. So now we have as you can see right here, we have a list that only lasts 2.5 seconds. And it's a lot easier to view if we actually plot the data. So if we go ahead and do the raw.plot function to plot our original data, we're going to get a window with our data, as you can see right here. You can see that we currently have data that goes from 0 to 10 seconds in this specific window. But as you can see down here, our entire array goes from 0 to 60 seconds. And you can kind of move down and view different sections. So, but if we do raw underscore selection and access the new variable and plot this variable, plot this data, then we get another plot, same channel types. However, now we have a selection of data that only goes from 0 seconds to 2.5 seconds, just as we intended. So we can see that we did in fact crop the data. One other thing So you can also extract data from objects. You can extract channels, individual channels or certain channels. And you can also extract the data by type. So as we mentioned before, we have 3 different types of data: MEG, EEG, and EOG. So if you only care about one type, in our case, probably EEG, you can extract that data. So this top code, which I won't run since it's pretty self-explanatory, just goes over how to extract individual channels. In this case, we're extracting 2 channels and plotting them together. So this top code, the channel names, just creates a list of the channel names that we're interested. Then the second command right here, 2meg channels, indexes the raw variable using the channel names, and also in this case, start sample and stop sample would just be a list of times and indices that we're interested in. Y offset is just more of an aesthetic, it's graphic. So this is what separates the 2 channels, rather than otherwise they would both be on the 0 line. Then the X variable creates a list. The X and Y create lists of the channel indices and of the actual channel data. And then these last 2 just plot the actual data. So as you can see here, all of that results in 2 channels that we're interested in, the ones MEG 0712 and MEG 1022. And they're plotted against each other and plotted together in the same figure. We can also extract channels by type using these commands right here. So in this case, we're only interested in the EEG channels, so we can create a variable EEG channel indices and use the function mne.pick_types. Make sure we're accessing the raw info object. Then here, this is where we actually choose which channel types. So in this case, we put MEG equals false. We could also put EOG equals false, since we don't want either of those data, and we put EEG equals true, since we do want to access that data. So let's see, let me run that. Oh, spacing. There we go. Then, once we create a list of indices, we can run the second command, eegdata.times, and we'll create a 2D array that uses the EEG indices as the times, and we'll index the raw variable to access the data from the channels we're interested in. This creates a 2D array, and then if we run the command eegdata.shape and print that, then we can get the size of our array, where 58 is the number of channels and 36,038 is the number of samples that we have in our list. One other thing I do want to add is that the fact that you can add annotations to your data. And that can be kind of important to kind of keep track of things and make things easier along the line. Taking notes is important. And you can add annotations 2 ways. You can add it in the GUI on the actual plot or on the command line. So we're going to go ahead and do that in the command line first. So the first thing you want to do is create a variable or an object that will hold your actual annotations. And you can do that by doing the mne.annotations command. So in this case, the list we have here, the first list onset is basically the start of where we want our actual annotations to start. So starting at 3 seconds, 5 seconds, and 7 seconds. Duration is how long you want it to last in seconds. And then description is the name that you want to attach to the annotation. So each first object in each list will basically result in a single annotation. So the first annotation is going to start at 3 seconds, last for 1 second, and will be labeled first. So the first thing we do is run that command. And then if we just want to verify that we actually created our annotations, we can print this variable, and you can see that we have 3 segments of annotations labeled first, second, and third. Then to apply our annotations, we can run the command raw.set_annotations. and pass our annotations list as an argument. Kind of get the confirmation here. And then we can go ahead and plot. In this case, we're only interested in a certain portion of the data, so we only need to plot from 2 to 8 seconds. And as you can see here, we printed our data, and you can see our annotations. So we have the first annotation, which lasts for 1 second, our second annotation, which lasts for half a second, and our third annotation, which lasts for 0.25 seconds. Alternatively, while we're here in the GUI, once you have this interactive plot pulled up, you can also press A, and then you should get this window so that you can add annotations in the GUI. So as you can see here, we have our existing annotations, first, second, and third. We can also hide them. In this case, I don't want to see the first one. And we can also add new annotations, and as well as create draggable edges. So in this case, currently I'm clicking on the first annotation, and if I drag onto the actual plot, I will create another annotation called first. I can also combine annotations by creating a new annotation that covers both of them. Oops. There we go. Or dragging the edges to overlap. And now I have one big first annotation. So if I want to create more annotations, I can also add a new label. Currently, the new label is bad, but if I wanted to, I could change that right here. But I'm going to go ahead and add a bad label. So if I add a new label called bad, now that it's clicked, I can also go ahead and add a bad annotation. So this section will be now labeled bad. This is also, which we'll talk about more later, how you can identify any bad data. By default, the annotation is bad underscore, and any data that is labeled or within this annotation won't be used in later functions. All right. So moving on to the bulk of what today will be about is signal preprocessing, which, if you remember from last time, signal preprocessing is the preparation of data for analysis, and it is the most important part. This probably will be the longest video of this project because it's the most topic heavy and the most important you need to actually practice. All right. So starting off with artifact detection. Artifacts themselves are portions within the recorded signal that originate from sources other than the one that you're trying to measure, basically noise. And these can be biological, environmental, or instrumental. Biological would be something like if you accidentally record muscle movement or heartbeats while you're trying to record brain activity. Or alternatively, if you're trying to record brain activity, if you record brain activity not relevant to the experiment. So like blinking or head movement, you can't really stop that, or sometimes you don't want it. Instrumental would be any sensor recording errors, interference between the sensor and the machine. And environmental would be something like power line interference, 50 or 60 hertz, depending on where you live, and any electromagnetic fields that may be affecting the actual recording. So, M&E has a lot of built-in tools to help you identify and later remove these artifacts if you want. The first thing we have to do is delete the projections, since the projections are there to help protect the data and help unnecessary or unintended alterations. We need to get rid of them. So we delete the projections, just get this little confirmation. And in this case, certain artifacts are more visible in different types of data. In this case, we're going to be looking at low frequency drifts, which are most clearly seen visually in the magnetron channels. So we're going to do the pick types. And in this case, we only want the mag. Then we can go ahead and plot it. All right. And let's see, let's let the data load. Perfect. And as you can see right here, These portions where you can see clear white space in the middle, those are the low frequency drifts, and usually they're caused by instrument. They're usually instrumental, but they're also affecting our data, and we don't necessarily want those. So later we'll talk about how to get rid of them, but first of all, you need to actually figure out how to find them and where they are. These are pretty easy to find visually, and so plotting is usually the best way to do that. Other stuff is a little different, easier to find. So in the case of AC interference, we can go ahead and plot, which would be anything, AC interference would be anything like power lines. We can see here, we ran a command to plot, and these are and we have the 3 different types of data, and we can see that it is more visible in certain types of data, in this case, the magnetometer, than the EEG or the radiometers. And the power line interference would be these spikes that you see happening right here. And M&E makes it really easy to find those, usually by plotting. As we mentioned before, you can also have noise for heartbeats. In this case, we're going to create just some epochs just to, again, easily identify the noise that we don't want. There we go. All right. Then we're creating some data that we can plot. Then if we go ahead and plot these, combining the data, we can see here. So we have radiometers, the magnetometers, and then the EEG. And these dotted lines are basically, and these spikes are where you would see the actual heartbeat noise. If you're familiar with the PQRS signal, this is what we're picking up right here. And you don't necessarily want it. As you can see, it's more visible in certain types of channels. It's not that visible in the EEG. So we might be okay. But if we were looking at the radiometers, it's very visible there. And so there we might need to get rid of it. As well as if you're recording EEG, you might record some ocular artifacts, which would just be like blinking or some other unintended noise. And we can do that by creating some EEG epochs, which, if you remember, epochs are just equal chunks of time and data. So if we run the commands here, this is just going to create a plot so that we can actually view our data. And again, this dashed line are the actual noise. As you can see, they're not visible in the radiometers, not visible in the magnetometers either, but they are very visible in the EEG, which makes sense. You know, our eyes are kind of close to our brain. So there's this dotted line right here. And that might be something that we want to get rid of later. But for now, we're just trying to identify it so that we can actually know what to remove. Yeah. So moving on. Now that we found the bad data and the bad, or any bad channels, bad sections of data, now what? Now we need to do something. As we saw before, you can label certain sections of data as bad. And if you annotate these certain sections as bad, M&E will automatically exclude it from being used in later steps. Or alternatively, we can also reject data and sections of data with our own criteria. So when we create epochs, or if we're trying to create epochs, we can create these rejection criteria. And the flat criteria is basically just letting M&E know what we consider to be flat. So if the majority of our data is around, say, 1 to the -5 volts, that can be considered flat even if it's not 0, but it's just around what we would consider normal noise. And we can use the reject criteria to reject anything above a certain level that we don't want to see. And then when we go ahead and create these epochs, which again are equal chunks of time of the data, it will, and we can pass the argument. In this case, what we're also doing is, well, I'll explain in a bit, but we can pass our rejection criteria and M&E will automatically avoid using the rejected data in the epochs. And this plot log at the bottom basically just is a chart that summarizes what parts of epochs were dropped. So to run this, I'm going to first go ahead to run this. The first thing I'm going to do is I am going to upload some new data just so that we're starting fresh. All right, perfect. And this time I'm going to upload the events. So to create epochs and more importantly, to actually view the data and when we would actually need to reject things, more likely doing an experiment. So to accurately simulate that, we're going to upload the events, which we saw how to do in the last one. And then we can add our events to our data. Now that we've added the events, now we can include our reject criteria and our flat criteria so that M&E knows what we consider to be flat and what we want to reject. Perfect. So now we've created those two variables. When we go to create epochs, some of these arguments that we'll be using. So we are using our raw data and we are using the events to superimpose the events onto the raw data so that we can actually see what's happening in the experiment. And what tmin and tmax will do is they will create epochs surrounding those events. So if we have an event that occurs at time 5, the epoch will start at negative 0.2 seconds before. So it'll start at 4.8 seconds and it will last for 0.5 seconds, more than 5. So it'll go from 4.8 seconds to 5.5 seconds. Here we have reject, as you can see here, we have reject by annotation equals false. But if we put true, then it would just reject any data that we labeled bad. Preload, just preloading the data, we want that to be true. And as you can see here, as I mentioned before, we have our reject criteria and our flat criteria. So here we can see that we uploaded the data and we can see that we rejected a bunch of epochs based on the criteria that we input. So if we want to go ahead and see in more detail, a little bit more detail what was dropped, we can run that command plot drop log. And here we have a chart that shows what data was dropped and how much of an epoch was dropped. So in this case, there's an epoch at channel EOG621 that we dropped about 2% of it because it was over our reject criteria. And as you can see, we have a bunch of other channels that parts were dropped of. And that is how you reject criteria, reject data. Alternatively, as opposed to bad sections of data, we can also have bad channels of data, which can be annoying if not dealt with, and especially can, more importantly, affect the results or your experiment. And so knowing how to identify them and how to delete them or fix them can be useful. And as we saw before, M&E can mark bad channels for you. We can also add to that list and either delete or add other channels that we feel are good or not good. And then M&E, as I mentioned before, M&E will automatically exclude anything that's labeled bad. So first thing we want to do is, again, I'm going to upload some new data or re-upload the data just to make sure that we're all good. Okay, so as we saw before, we can print bads, and these are the channels that were labeled bad automatically by M&E. And as you can see, this is a list, which is basically an array. So we can go ahead and run some commands. In this case, I'm going to create a copy of the bads list, just so that any changes I make won't affect the original list. And then we can work pretty easily with a list in Python, kind of similar to how you would work in C++. So if we want to add another channel, we can do raw.info access bads .append, which will add another bad list. And in this case, we want to add EEG 50. So if we run the command and we print bads, now we can see that we've added EEG 50 as a bad channel. If we want to add multiple channels at a time, we can do .extend instead of append, which will add a list of channels. In this case, we're adding EEG 51 and 52 to the list. And again, if we go ahead and print it, now we can see that our list has been expanded by the 2 channels that we added. And of course, as opposed to just adding to the list, we can also go ahead and delete things from the list. So Python has a function for lists called pop, which will delete the last entry. In this case, we're doing -1, so it's going to remove the last entry of the list. And in this case, as you can see, the last entry on the list was EEG 52. We went ahead and popped it. So now it's no longer in the bad channels. Then, as you remember, we still have the original bads variable. So we can go ahead and also change the entire list at once. In this case, the current variable we're using, is called bad channels. And so our bads is currently a list of 4 different channels. But since we have made a copy of the list at the beginning, we can go ahead and change it all at once. And then if we print it, as you can see, we're back to the original list that we had of bad channels with only 2. So one other thing you can go ahead and do in M&E, and M&E has tools to help you do this, is that you can interpolate bad channels. And so what that means is rather than excluding a channel, you can attempt to fix the channel. And so interpolation is basically the process of using surrounding electrodes, and assuming you know their location and what they and assuming they work, you can use the data that they recorded and the known locations to kind of estimate what the bad electrode or the bad channel may have looked like. And so then you can interpolate the channel and then go ahead and use it for later in your experimentation. So to do that, the first thing we're going to do is crop our data just so that we don't have to work with as much data, so that things go faster. You can see just confirmation again. We're going to create a copy of our data, but specifically we're going to focus on the EEG channels. So create a copy, and in this case we're excluding everything except for the EEG channels. And exclude this last argument right here, exclude. This is the, you don't have to always include this, but this is the argument that allows you to exclude by annotations. So by default, this is bad. In this case, we're not passing anything to the exclude argument, which means we're not going to exclude anything, even the bad annotations. Then we're going to create a new variable for our interpolated data, and we're going to create a copy, and then we're going to use .interpolate bads, and then we're going to set reset bads to false because we want to keep the channels. And then if we go ahead and plot this data, we can see the effect of interpolation. All right. So here we can see our original data. The black in the background are what the other channels would look like, and is what M&E is using to interpolate this data. And these red channels is the bad channel. So in this case, as you can see, whatever happened with this channel resulted in that it resulted in it not recording the data that we wanted. So you can see the red is a lot flatter compared to the surrounding channels. So what interpolation will do is it will take the surrounding data and we'll use it to kind of estimate what this red channel, the bad channel, should have looked like. So after we run the interpolation, you can see the red here looks a lot different. Looks more similar to the surrounding channels. And then now that we've fixed the channel, we can go ahead and use it in later processes. One other thing that we can do is we can also filter and resample our data. We talked about filtering before in the first video, and resampling is also something that you can do. And it's really only useful when you, only need certain portions of data and you can afford to save some space. So basically, as you know, with EEG, we can record a wide range of signals, but a wide range of frequencies. But if we're only concerned about the low range, then we can always go ahead and resample. That way we can only focus on the low frequencies and avoid high frequencies. So resampling is usually downsampling because it's easier to go lower from what you did. It's a lot harder to go higher. But after you resample, makes it a lot easier. Saves space. So let's see. So first thing I'm going to do is I'm going to actually start a new session just to save some space and make sure everything's going all right. So I'm going to do basically everything I've done before. I'm going to import the necessary libraries, and I'm gonna crop my data just to save some space. Perfect. All right, data's loaded. So in this case, let's say we want to, as we saw before, we saw the low frequency drift noise. And let's say that we want to get rid of that low frequency drift since it kind of affects our data. And we saw that it was most clear in the mag channels. So we're going to go ahead and pick just the mag channels since that's where it's most visible. All right. And let's go ahead and plot it just so that we can actually see the low frequency drift again. And we can see what we want to get rid of. All right, so here we have our data. As you can see, the low frequency drift happens right in the center, probably around maybe 26 seconds, up to about maybe 35, or actually it goes all the way to 40 seconds. And so we want to go ahead and apply a filter to this. So the first thing we need to do to actually, oops, let me get rid of this. First thing we need to do is we actually need to create the parameters for our filter. So we can create a new variable, which in this case we're going to call filter params, and we're going to use it. We're going to enter the function filter.createFilter and use that function to enter our parameters. So in this case, as you can see over here, it's the same command on the PowerPoint. We're going to load the data from raw, and we also need to pass our sampling frequency as an argument so that the filter, we have a base frequency. And in this case, we're going to create a high pass filter, and we're going to cut off everything underneath 0.2 hertz. The high frequency, this is a single-sided filter, so we don't need a high frequency. If we wanted to create a band pass filter, we would just enter in our top cutoff frequency, and we could go ahead and do that. So if we run the command, you can see we output some information that we designed a filter where it's going to be applied, the low pass band, and then the filter length, everything. If we wanted to go ahead and see what our filter looks like and what it'll actually affect, we can run this command .viz.plotFilter, enter in our filter parameters, and we can see what our filter actually looks like. Some of you will be familiar with this, but yeah, so we can see here that we have our cutoff frequency at about 0.2. We have the -3 decibels, or the 75%. And yeah, so we can go ahead and apply that to our actual data by creating so we're going to create a copy of our data just so that we don't affect anything. And we're going to name this new variable raw high pass since we just created a filter. So we create a copy, and then we filter this data using the low frequency and the high frequencies that we set, which in this case, low frequency is 0.2, and we don't want a high cutoff. So we can run that. As you can see, pass the filter, And then if we go ahead and plot this filtered data, we can see how it affects our low frequency drift. So if you remember what the low frequency drift was, now that we went ahead and cut off anything underneath 0.2 hertz, we've gotten rid of a large part of our low frequency drift, which this makes our data a lot more usable. We can also resample our data. And if we only care about, as we mentioned before, we only care about certain portions, certain frequencies that are contained within our data. So we can create a new variable for the downsample data. And downsampling is pretty straightforward, or resampling is pretty straightforward. We just create a copy so that we don't affect our original data, and we do .resample, and then we set the sampling frequency that we want. In this case, we're going to do 200 hertz. Enter the command, and that's pretty much it. Here we just have some information about the data that was found. We have the events, and then we can go ahead and plot. This command is going to plot our original data and our downsample data. All right. So here we go. I believe this is the downsample data. These dashed lines are about where the cutoff is. But as you can see, this is our data, pretty straightforward. It's going to look about the same. It just has a much lower frequency. And then here is our original data. As you can see, there's a lot more that was recorded here. But the general information is still about the same. It's just that this particular data has a lot more information contained in it that we might not necessarily need, or that we could avoid. And that is how you downsample your data. Pretty straightforward. Okay. So moving on to setting or changing your EEG reference. So EEGs specifically, and other different types of instrumentation, such as MEGs or I forgot what the muscle ones are called, but who cares? They measure a voltage difference. Specifically, they measure a voltage difference between the electrode you're interested in and a reference electrode. And the reference electrode can vary. Usually it's pretty far away to try to get the least amount of noise. But sometimes you can have a virtual reference or pretend there's a reference. So having a reference is pretty important, especially if you want to see the difference in the electrodes and what they're recording. So first things, and we can, and in M&E, we can go ahead and set our own reference or change the reference if we're trying to view certain things. We can also use the average of all of our channels as a reference if we want to view how each channel is different from a specific channel. So first thing I'm going to do again is I'm going to go ahead and basically just reload my data just to make sure we're all on the same track. So I reloaded my data. In this case, and I'm going to run this command, which is going to just pick certain parts of the data that we want. And so let's say we want to add a new reference. So we can go ahead and add an entire new channel completely by using the mne.addReferenceChannels function. In this case, we're adding it to the raw data, and we're going to pass a list of ref channels that we want to add. In this case, we're just going to add one new channel, which, let's say this is our reference channel, that we're going to call EEG 999. So if we run this command, now we've added the channel. And if we go ahead and plot our data, you can see the newly added channel. So as you can see right here, we have all our EEG channels. In this case, we only wanted to pick, we only care about looking at the EEG. And down here in the bottom is our newly added EEG channel, which is a gray flat line. Up here, as you can see, EEG 53, this is our actual reference channel that we are using in the data, but we went ahead and added a new one. Sometimes you want more than one. and you can usually identify the reference channels because they're going to be flatter, because this is basically taking the difference between the reference channel and every other channel and the reference channel. So obviously this minus itself is going to be about 0, and they're usually grayer. So now we've added a new channel, and let's say we want to change our reference. Let's say we no longer like EEG53 as our channel. We can set a new reference channel by passing the argument set_EEG_reference. And we can add our channel. In this case, let's say we want to change our reference channel to EEG50. Then we can go ahead and plot this data again. And you can see our data changed completely. So what happened is now, and you can see EEG50, our new reference channel, is flat, because we are taking the difference between every other channel and this channel. And again, this minus itself is going to be flat. So now we can see that we've changed our reference. We can also make a kind of a virtual reference by taking the average of all the channels and using that as a reference, which is kind of useful if you want to see how each channel is different from the average. So we can create a new variable, raw average ref, create a copy of our original data, set the EEG reference, but this time for our argument, we're going to pass ref channels and pass the string average, which will let M&E know that we want to use the average of all the channels as our reference. Then we can go ahead and plot this again. And we can see that now we have used the average of all the channels as the reference. So we can see all of our channels are a little different from what they looked like last time. And that's because we've changed our reference. And that is how you set your reference or change the current reference that you have on your EEG data. And the last thing we're going to talk about today is creating data epochs. So as I mentioned before, epochs are chunks of an original signal that can be treated similarly to raw objects. So our raw data, as you've seen multiple times today, can tend to be pretty long, and sometimes we don't need all that data. So we can go ahead and create epochs pretty easily in M&E. First thing, of course, we want to do, which I will go ahead and do one last time, is upload our data again. In this case, I'm cropping the data since we don't care about all of them. And M&E creates your epochs based on your events. So of course, we want to go ahead and upload our events and add those to our raw data as we've done previously. So we can go ahead, once we've uploaded our events, now we can use this M&E.epochs function to create the epochs that we care about. And we pass the argument, so it's going to use the raw data to create the epochs, and it's going to create the epochs around the events the events list that we've passed, as we saw previously. And so in this case, let's say we have an event at 10 seconds, and tmin is going to start the data epoch at 9.7 seconds, minus 0.3 seconds before the event. And it is going to last for 0.7 seconds after the event. So in this case, it will go from 9.7 seconds to 10.7 seconds. And so it'll create epochs of that duration around every single event that M&E can identify. So we went ahead and created, using these events that were found from our simulation channel. Then we can run the epochs command to create our actual epochs and insert them into a new variable, which we're just going to call epochs. There we go. Then we get some information about what was happening, setting the baseline, and just confirmation. And then we can go ahead and plot our epochs. In this case, I'm going to only plot 10 epochs, but we can plot all of them or any number. All right. And here we go. Here are our data epochs, which are centered around each one of these spaces between the dashed lines are our epochs. So as you can see right here, we do in fact have 10. They're all labeled sequentially underneath. And then these are underneath, we can see all the epochs that were created for the entirety of the raw data. So we have about 90 for, I think, maybe 85 epochs. So let's say if we want to go ahead and only view one epoch, say we only care about a certain one, here we go. Now we only have one epoch centered around 0, which was the first where the first event happened, minus 3 seconds, plus 0.7 seconds. And that is how you create data epochs. We can also view each one of them individually if we wanted to. So here we have, we're at epoch 42, epoch 55, and we can view all of them individually as opposed to having to view big chunks of raw data. That is how you create data epochs. And every function that we run using the raw data, we can run using epochs instead of the giant raw data. And that's it. That is pretty much everything I wanted to cover today. That is how you pre-process EEG data or any type of data, any type of biophysiological data, specifically EEG data for us, since we are concerned with that mostly. And that is how you pre-process it in MNE Python.